We're going to do a crash course of logarithmic functions. I say crash course. A lot of you guys are going to see familiar stuff from last week, but let's get better definitions down. So I've got decent definitions. For example, logarithmic function is defined as log base b of a equals c. So now you have it in printed form. And then where b is the base, a is the argument, and c is the exponent from exponential form. Now, hold on. Wait a second. I just realized that's not how we learned it last week. We had log base b of some number is the power. That's how we learned it last week. And we had to figure out base to what power is the number. Base to what power is the number. All right.
So A is n and then c.
Yeah, whatever number's in this position is called the argument as well.
Is it going to be switching or is it just going to always be A and c then?
I think you can have any letters here. Some math books that you might see in college algebra use X and Y, or Y and X might be switched. So you just have to realize this will probably always be B, because they like to use that for the word base. But these will be interchanged. But base to what number, base to what power is the number. All right, let's go through some examples going from logarithmic form to exponential form. And let's write our way that we learned last week. So I'm going to cross some stuff out. So this is what we saw last week. Log base b of n equals p. And then we had to ask ourselves, okay, base to what power is the number? Base to what power is the number? We're going to practice rewriting from one form to the other. Like, what's it going to look like? So to rewrite log base 3 of 9 equals 2, the form, if you haven't done so already, 4. All right, so log base 8 of 4,096 equals 4. In the next one, you've got to figure out what's the base position. So log base 1/2, and 1/2 is going to be raised to what number? So 1/2 to the negative second power is equal to 4. We could look at this as the circle, a great circle. 1/2 to the negative second equals 4. 8 to the fourth equals 4,096. 3 squared equals 9. Like, you see that circle? Sometimes that circular motion helps us convert from one to the other. Excuse me. So, I can also rewrite using the circular motion. Using the circular motion, log base 2 of 4,096 should equal 12. So that circular motion works both times. And you can check that. Like, does the circle work? 2 to the 12th equals 4,096. So that circle, as long as everything's on the left. That's the other thing. The circle works when everything's on the left side. Like the logarithm is on the left side. The exponential piece was on the left side. That's where that circle comes in handy. But that's for my visual learners. For my audio learners, you like the word base. If you can just identify the base, everything else kind of falls through. The power, you can figure out the power position. All right, let's see the next piece. Oh, I skipped a slide. Thank you. Okay, let's rewrite. So because we don't know the power, we're going to figure out what it is. So let's rewrite the expression to evaluate. So doing this circle, 5 to what power gets you to 1/25th? Again, we don't have a complete sentence here, so let's set it equal to a power and then rewrite it in the other form. 8 to what power is 1? So that power has to be 0. So let's get common log. Now we actually have it written down. That's my bad. I went through a little side note on it. But notation, you're just going to see it as log with a number off to the side. There's not going to be a base. So I don't know if you guys remember that quiz that I made you take on Google Classroom where you were like, hey, there's nothing written here for the base. What should we assume? And now I'm giving you an answer. You should assume base 10. So, example, if we had log of 100, that means, so I'm going to need to complete that sentence, common log of 100, that means base 10. So 10 to what power gives you 100? 2. And then not an example, if you had this, let's see, not an example. Hold on. So if I put in my calculator common log 2, it won't equal 4. So if I hit common log 2 in my calculator, it's not going to be 4. And 2 to the 100th power is not equal to 10. So these are decent, not common logs. All right, natural log has a natural logarithm of base e. So here, there's two notations. We may see log base e of 4. That could be 1. Or you might say ln of 4. Both of those are equivalent expressions, not equations. So a decent example, we could do natural log of e squared is equal to 2. And not an example? Ooh. Well, natural log of e squared is not equal to 1. I don't know. I need a non-example. So here's another one. Logarithms and exponentials undo each other. So if you see, and again, these are expressions, so I'm going to complete the sentence with an equal sign and variable. But log base b of b to the power, we're just left with the power, c. And same here, if we have base to the power, log base b of a, we're actually just going to be left with a. So when I see an exponential and a logarithm happening at the same time, it's the same inverse relationship as if I saw that. So this inverse relationship is the same as if I saw a square root and a square happen to the same number at the same time. Now notice how there's nothing else going on, like there's no plus sign or like a minus sign anywhere. Like it's just, we're only dealing with bases. Those are the only numbers I see with a logarithm somewhere. All right, next, simplify. I notice in the problem log base 3 of 3 to a power. That undoes each other. So I'm going to complete the sentence is 5. Oh, this is a little hard. 10 to the log 5. Simplify the expressions. That's just it. Is there any other way that I can rewrite 10? Because here, wait a second. What's the base of this log? Notice how there's no base written. Notice how there's no base written. So let's put this in. 10 to the common log base 10 of 5. Now I can see the rule a lot clearer. I see the two bases match. So I'm left with just the argument. It's equal to 5. Yeah.
How'd you get down to 10?
Hold on. Common log, if I don't see a base written, because technically this 5 is in the same position as the L. Like, if you only see one number after a logarithm, then that means that's the argument, not the base. All right, let's try rewriting this 10,000. Oh, and what's the base of this log? It's log base 10, so is there any way I can get 10,000? Rewrite 10,000. 10 to the 4th to the x. What happens when you have a power to a power, right? Those rules of exponents are never leaving us. You multiply those. So you've got log base 10 of 10 to the power 4x. And you've got the bases that match. So I'm just left with the power, which is an expression for x. So let's talk a little bit about what is the inverse of a logarithm. Let's say, to find the inverse, last chapter we would switch the domain and the range. To solve for y, I have to get rid of this function log base 8. Well, in order to be left with y, I would need an exponential of log base 8. I can do this two ways. Either raise both sides to be a power of 8, or I could rewrite. But raising both sides to be a power of 8, 8 to the log base 8, just leaves you with y. So this is the inverse. Y equals 8 to the x. The reason why we're going to concentrate on inverses is I know how to find a table dealing with 8 to the power of x. I plug in -1, 0, and 1, plot those points. So I also know if I can plot these points and then just switch the domain and range, x's and y's, I can plot those as my points for this logarithm, since I can't plug it into my calculator yet. So let's say we had to find the inverse of this in order to graph and then switch domain and range. So switch x and y. We would have to subtract 2 first. So what does that look like? X minus 2 equals 3 natural log y minus 10. I still don't have the natural log completely by itself, so you're going to have to divide by 3. You have to get rid of everything that is outside that logarithm. Outside that logarithm. So divide by 3, what does that look like? Well, I'm just going to keep it as x minus 2 divided by 3 equals natural log of y minus 10. So because this is log base e, in order to get rid of that function, I have to do an exponential. So we're going to raise both sides to be e to their power. On the left power and the right power. So we have e to the x minus 2 divided by 3 equals y minus 10. And then I get y by itself by adding 10. So the inverse of y is this crazy looking deal, and then plus 10. All right, so graphing logarithmic functions, you already have all this written down, so why don't you just watch for a moment? Don't worry about writing anything down unless you want to like a little tidbit of, hey, here's what this means. Okay, so we're going to use exponential tables of the parent graph with the base in the equation. For example, let's say I wanted to graph log base 2 of x. Well, guess what? Can't plug those numbers in my calculator, so how am I going to do it? I'm going to figure out the inverse. What is the inverse? Does anybody know what the inverse of is? Well, I guess you can look at your paper. The inverse of y equals log base 2 to the 2 of x is the exponential base 2 to the x. All right, so we're going to start there. We're going to graph, or we're going to figure out the table of y equals 2 to the x. Plug in -1, plug in 0, plug in 1. Well, notice how I give you that table already in your notes. And we know that inverse functions switch domain and range. So then that means I'm going to switch that table. I'm going to flip the domain and the range and graph those points. Now, something that is not on your paper, we also need to recognize the asymptote. Do you remember what the asymptote was in an exponential graph? Yeah, not only that, it was horizontal asymptote, y equals 0. So now we're going to have a vertical asymptote. Notice how the horizontal word now becomes vertical? And instead of y equals, it shall be x equals 0. So, by the way, the old graph, y equals 2 to the x, now gets a shape. This is the logarithmic shape. You already have this in your notes. So this is the basic shape. Now the bad thing is, this is the logarithmic with a growing base. This is a growing base. So if I had a decaying base, it would be flipped around looking like it would be decaying. All right, let's look at another table. All right, so if I needed to figure out this function, I would have to find the inverse. So if I was trying to find the inverse, I'm going to switch x and y. I realize, okay, that plus 4 is outside the function, so I'm going to subtract that first. And then how do you get rid of that logarithm? So that base 1/2 is going to now be my base on both sides, but I'm going to have exponents. Oops. I'm looking at the inverse. I'm going to have to graph 1/2 to the x minus 4 and then switch domain and range, or switch the x and y in the table, and then graph those points, because you can't just do a t-chart. You can't do a t-chart with this because we don't know how to plug that into our calculator. All right, so now notice your tables in your notes. Your tables start going with 1/2 to the x power. They use that as their main function, 1/2 to the x power. Plug in -3, -2, -1, 0, 1, 2, 3. But in our notes, like last week, we only did -1, 0, and 1. And then, wait, it was -4 in the exponent. -4 in the exponent means you're going to have to, oh, I did, my bad. Oopsies. Oh, good thing we're going over this, eh? Oh! Oh, hold on. So what I just made you go through over to the side was we did this, and then we subtracted 4 from the exponent, so we stayed in exponential form to figure it out, and flipped domain and range last. Here they flip domain and range in the beginning, and then add 4 to all the outputs. All right, well, and this is actually the graph that it becomes. Since the base was 1/2, you're at a decay base, or a decaying factor. So this is actually decaying. Notice how the vertical asymptote, wait a second, vertical asymptote, well, the horizontal asymptote here would have stayed at y equals 0. So then when we switched, the vertical asymptote would have been y equals 0. Because only the